built around a star would experience time differently on its inner and outer edges. Imagine opening your eyes beneath a sky that should not exist. Above you, there is no ordinary horizon, no blue curve fading gently into distance, no familiar planet bending away under your feet. Instead, the land rises. It rises in both directions like a road made for gods, climbing into the heavens until the ground itself becomes a shining arch across the sky. Far ahead, beyond oceans, continents, forests and cities, the same world curves upward and returns as a thin glowing ribbon overhead. And at the center of everything, not above you, not below you, in the ordinary sense, but suspended in the impossible middle of this cosmic machine, burns a star, a real star, a sun captured inside architecture, a living furnace surrounded not by planets, but by a single colossal ring, a band so enormous that billions of worlds could be imagined upon its inner face. Now, ask yourself a quiet question before we go any deeper. If such a ring world existed, if people lived not on a planet, but on a rotating band around a star, would time pass the same everywhere on that ring? Would a child born near the inner edge age at exactly the same rate as a child born near the outer edge? Would clocks agree across the width of this artificial world? Or would the structure itself divide reality into slightly different rivers of time? Stay with this thought, because the answer is stranger than it first appears. And before we step onto this impossible road around a star, like the video, subscribe and tell me in the comments where you would choose to live. Near the inner edge, closer to the star and its golden pull. Near the outer edge where the ring races faster through space. Or somewhere in the calm middle where civilization might try to pretend that time is simple. At first, the idea sounds like science fiction only. A ring world feels like something too huge to be discussed seriously, too grand to belong in the same universe as bolts, steel, dust, oceans and human breath. But the beauty of physics is that even impossible architecture must obey real rules. You can imagine a bridge around a star, a palace larger than planetary orbits, a band of land so wide that its weather systems become legends. But once you place it in the universe asks for payment. It asks for gravity, speed, energy, stability, material strength, heat flow, radiation shielding, clock synchronization, and relativity. A fantasy shape becomes a physics problem. And that is where the wonder begins. Because a ring world is not just a bigger space station. It is not a planet stretched into a circle. It is a machine that tries to replace nature. It tries to do what planets do automatically. Hold air, hold oceans, hold living beings, receive sunlight, create day and night, and give every creature the feeling that down is real. But unlike Earth, the ring world cannot simply rely on a massive ball of rock beneath your feet. Its gravity, if it is to feel like Earth's gravity, must be created by motion. Picture the ring turning around its star. From far outside, it looks almost peaceful, like a thin circular line, spinning in darkness. But peaceful is the wrong word. Every city, every river, every mountain, every person on the inner surface is moving sideways at enormous speed. The floor is not still. The land is not resting. It is sweeping around the star in a gigantic circle. And because your body wants to keep moving in a straight line, while the floor constantly curves away beneath you, you feel pressed against the ground. That pressure becomes your weight. That sideways motion becomes your artificial gravity. Down on such a world is not a direction given by a planet. Down is a negotiation between your body's inertia and the ring's rotation. If the ring spins at the correct rate, the people living on its inner surface may feel something close to Earth gravity. They may walk, sleep, build houses, pour water, and plant trees as though they live on a natural world. But under every ordinary movement is a hidden truth. They are standing on a cosmic centrifuge. Now this already introduces the first twist. On a spinning ring, the inner edge and the outer edge do not move in exactly the same way. Imagine a running track. Two runners start side by side, one on the inside lane and one on the outside lane. If they must complete a lap in the same time, the outer runner has farther to travel. The outside lane is longer, so the outer runner must move faster. A ring world works in a similar way. If the whole structure rotates together, the part farther from the central star travels around a slightly larger circle. In the same rotation period, it covers more distance. That means the outer edge has a greater tangential speed than the inner edge. This difference may seem small compared with the whole size of the ring, but when the structure is astronomical in scale and moving at incredible speed, even a small difference becomes a real physical fact. And according to special relativity, speed changes time. A moving clock ticks more slowly compared with a clock at rest in the chosen frame. The faster the motion, the stronger the effect. So the outer edge of a rotating ring world, because it moves faster, would experience slightly slower time from the effect of motion. But here comes the second twist, and it pulls the story in the opposite direction. The inner edge of the ring world is closer to the star, not by the entire orbital radius, of course, but by the width of the ring. If the ring is millions of kilometers wide, or even far less than that, the inner edge is still measurably deeper in the star's gravitational field than the outer edge. General relativity tells us that gravity also changes time. Clocks deeper in a gravitational field tick slower than clocks farther away. A clock near a massive object runs differently from a clock far from it. This is not poetry, it is not metaphor, it is part of how the universe works. So the inner edge, because it is closer to the star, also has a reason to experience slower time. Now the ring world becomes a quiet contest between two versions of relativity. Motion says the outer edge should tick slower. Gravity says the inner edge should tick slower. The world has two edges, and each edge has its own claim on slowness. This is where the question becomes beautiful. Which edge wins? Which side of the ring world ages less? Is it the inner edge, sitting deeper in the star's gravitational valley? Or is it the outer edge, racing faster around the star? The answer depends on the exact design. A ring world is not one single object, with one single possible size. It could be narrow or wide, close to the star or far away, spinning gently or rotating at terrifying speed, built around a small red dwarf or a sun-like star, designed for Earth-like gravity, or something weaker. But in many large rotating ring world concepts, especially one built at a comfortable distance from a sun-like star, and spinning fast enough to provide Earth-like artificial gravity, the speed effect across the ring's width can be more important than the tiny gravitational difference across that width. In that case, the outer edge may actually age slightly slower than the inner edge, even though the inner edge is closer to the star. That is the kind of answer that feels backwards at first. We expect closer to the star to mean deeper gravity and slower time. But rotation adds another layer. The outer lands are not merely farther away, they are moving faster. And in relativity, speed is not just motion, speed is a way of spending time. Now imagine a civilization living on this ring. They may not think about relativity every day. A farmer near the outer edge may rise under artificial dawn, tend crops in soil engineered from asteroids, watch birds fly beneath a sky crossed by the distant arc of the ring, and never feel that time is strange. A child near the inner edge may run through gardens, attend school, grow older, fall in love, and never notice that her heartbeat is ticking inside a slightly different rhythm from someone across the ring's width. Local life feels normal. That is one of the deepest lessons of relativity. Time dilation is not something that feels like slow motion to the person experiencing it. Your thoughts do not become syrup. Your breath does not feel delayed. A clock beside you ticks normally. Your body obeys local time. The strangeness appears only when separated clocks are compared. It appears in measurements, in signals, in records, in navigation logs, in legal systems, in scientific instruments, and in the slow accounting of years. So if you lived on the outer edge and your twin lived on the inner edge, neither of you would look across the world and see the other moving strangely. There would be no glowing aura of altered time. There would be no dramatic cinematic distortion. But if both of you owned extremely precise clocks, and if you remained in your different regions for a long period, and if the civilization carefully corrected for signal delays and motion, your clocks might begin to disagree by a tiny amount. Maybe not enough to matter over breakfast. Maybe not enough to change a birthday party. But enough for engineers, enough for spacecraft controllers, enough for the people who maintain the ring's rotation, stabilize its position around the star, coordinate traffic, run scientific observatories, and keep a civilization spread across an artificial world larger than anything humanity has ever touched. On Earth, relativity is already part of advanced technology. On a ring world, relativity would not be an abstract chapter in a physics textbook. It would be part of the plumbing of civilization. Think about what time means on Earth. We divide it into time zones because the planet rotates under the sun. Noon in one place is midnight in another. But despite our messy time zones, we can still imagine Earth as having one global time standard. The planet is small enough that, for ordinary life, we pretend that now is simple. On a ring world, that illusion becomes much harder. The circumference could be hundreds of millions of kilometers, perhaps close to 1 billion kilometers or more, depending on its radius. Light itself would need time to travel across it. A message sent around the ring would not arrive instantly. A signal from one city to another may arrive after seconds, minutes, or much longer if the distance is vast. And because the ring is rotating, the sender and receiver are not simply sitting still. The communication network is built on moving ground. Light travels locally at the speed of light, but the path, the arrival time, and the synchronization of clocks all become part of a rotating geometry. Now, imagine the ring world's internet. Not just a small network of cables and satellites, but a civilization-scale nervous system wrapped around a star. Every message needs a timestamp. Every financial transaction needs ordering. Every medical emergency requires coordination. Every spacecraft launch must know where the ring will be, how fast the launch platform is moving, and what clock standard is being used. If the inner edge and outer edge tick at slightly different rates, then the ring cannot simply rely on one naive clock. It needs layers of time. Local civic time for daily life, engineering time for maintenance, navigation time for spacecraft, stellar reference time for astronomy, legal time for contracts, biological time for medical records, perhaps even edge-corrected time, a standard that tells you how your local clock differs from the ring's chosen central reference. A ring-world civilization may not ask, "What time is it?" It may ask, "What time is it?" according to which frame, which edge, and which correction. This sounds complicated, but nature has already trained us with smaller examples. Satellites orbiting Earth experience both velocity-based and gravity-based time differences. Their clocks must be corrected, because if they were not, positioning systems would drift. A ring world would amplify this principle into a planetary-scale habit. The people there may grow up learning that clocks are local instruments, not cosmic commandments. A child might learn in school that time near the outer edge is not wrong, and time near the inner edge is not wrong. They are both correct locally. The disagreement is not a failure of clocks, it is a feature of space-time. In such a society, relativity might feel less mysterious than it does to us. We discovered relativity through experiments, equations, and shocks to common sense. They might discover it every time a train crosses from one radial district to another and automatically updates its clock correction. But there is another hidden complication. A ring world is not just rotating, it is rotating as a loop. Synchronizing clocks around a rotating loop is deeply subtle. If you send light one way around a rotating ring and light the other way, the two beams may not return at the same time according to clocks on the rotating platform. This kind of effect is connected to rotation itself. It is not because light changes its local speed. Locally, light still behaves according to relativity. But the rotating platform changes the global comparison. Imagine standing on a carousel and tossing two perfectly fast messengers in opposite directions around the rim. One chases the moving meeting point, the other meets it sooner. On a ring world, with distances so enormous that light travel time becomes a serious part of daily engineering, this rotational asymmetry could matter. It would affect global positioning, communication timing, telescope arrays, and emergency systems. Now let us slow down and stand on the ring itself. Imagine a road running from the inner edge to the outer edge. It may be hundreds of kilometers wide, thousands, perhaps far more depending on the design. This road is not like a road on Earth. It crosses not latitude but radius. With each step outward, you are slightly farther from the star and slightly faster in the ring's rotation. With each step inward, you are slightly closer to the star and slightly slower in tangential motion. You would not feel time changing beneath your feet. But in an extremely precise sense, every meter has its own clock rate. The world becomes a gradient of time. Not a dramatic waterfall, not a doorway into the future, but a gentle slope in the fabric of chronology. The ground is a clock face, and distance across it is also difference. The strangeness deepens when we remember that artificial gravity on a rotating ring also changes with radius. If the ring rotates as a rigid structure with one angular velocity, then points farther from the center have greater centripetal acceleration. That means the artificial gravity felt at the outer edge could be stronger than at the inner edge, unless the ring is designed in a special way, or unless the width is small compared with the radius. For a very large ring with a relatively narrow width, the difference may be tiny. But for a wide enough structure, the outer edge would not only move faster, it could also feel slightly heavier. The inner edge could feel slightly lighter. In daily life, that might shape architecture, sports, agriculture, and health. People near the outer edge may build lighter structures differently, design elevators differently, or even experience long-term biological adaptation to a slightly different effective gravity. The ring world would not be one uniform land. It would be a gradient world, gradient of light, gradient of artificial gravity, gradient of stellar distance, gradient of clock rate. At this point, another question appears. If the ring world is built around a star, why does it not fall into the star? The answer is subtle, because a ring world is not exactly orbiting like a planet. A planet falls around a star because gravity pulls it inward, while its sideways motion carries it forward, creating orbit. A ring world, especially a rigid ring centered on the star and rotating for artificial gravity, is not simply a planet in orbit. Every part of it may have motion, but the structure as a whole requires stability. If the star is exactly at the center, the gravitational pull from the star is symmetrical. But if the ring drifts off-center, the gravitational situation can become dangerous. A simple massive ring around a star is not automatically self-correcting in the comforting way people might expect. It may need active stabilization, engines, mass drivers, magnetic sails, gravitational control systems, or constant intelligent correction. In other words, the ring world is not a passive home. It is an ongoing act of control. And now time dilation enters the engineering again. Suppose sensors across the ring detect a tiny drift. The stabilization system must compare data from different locations, but those locations have signal delays and slightly different clock rates. If the ring is enormous, a command sent from one region may arrive after the structure has already moved significantly. The system must predict the future position of the ring, not merely react to the present. And what is present on a rotating world whose clocks do not perfectly agree? The control system becomes almost philosophical. It must build an operational version of now. It must decide which measurements belong together. It must correct for motion, gravity, and delay. If it fails, the ring could wobble, stress could build, or sections could experience dangerous acceleration. The civilization's survival may depend on a timing system more precise than anything ordinary people notice. This reveals a deeper truth. A ring world is not just a megastructure of matter. It is a megastructure of information. Its stability depends on knowing itself. Every section must know where it is, how fast it moves, how stressed it is, how warm it is, how its clocks compare, how its atmosphere flows, how its shadow systems work, how incoming debris is tracked, and how the star is behaving. A planet is held together by gravity. A ring world must be held together by engineering, feedback, and trust in measurement. If its clocks drift without correction, its sense of itself becomes blurred. A ring world that cannot keep time, cannot keep shape. Now let us consider the star at the center. From the living surface, the star may not look like our sun in the sky. Depending on design, it could appear as a brilliant disk always in a fixed direction, perhaps controlled by shadow panels that create artificial day and night. On a natural planet, day and night come from rotation. On a ring world, if the living surface always faces the star, then day may be created artificially by orbiting shade structures, rotating screens, mirrors, or programmed light systems. The sky itself may be engineered. Night is not simply absence. Night is a scheduled event. Dawn is not the planet turning. Dawn is machinery letting the star through. Imagine the psychological difference. People would not live under a sky that cycles naturally because the world turns beneath it. They would live inside a civilization that negotiates with sunlight. The inner edge, being slightly closer to the star, might receive slightly more stellar radiation than the outer edge. If the ring is extremely wide, this could matter for climate. The difference in distance from the star affects light intensity. Radiation spreads outward, so closer regions receive more energy. In a narrow ring, this may be negligible, but in an immense structure, it might shape climate zones. The inner edge might require stronger heat management, higher shielding, different agriculture, or more reflective surfaces. The outer edge might be cooler, calmer, or perhaps more desirable for certain habitats. But again, speed complicates the story. The outer edge may be cooler by distance, but more time-dilated by motion. The inner edge may be warmer and deeper in gravity, but moving slightly slower. Every simple expectation meets a hidden counter-effect. Would people choose where to live based on time? Probably not at first. Most citizens would care about climate, culture, economics, beauty, safety, and access to transportation. But over centuries, relativity might enter identity. Outer edge communities might joke that they are younger than everyone else. Inner edge people might claim they live closer to the true heart of the ring, nearer the star that feeds all life. Middle regions may call themselves balanced. Legal systems may define age by local proper time, while interregional institutions use standardized time. A person who travels frequently across the ring could accumulate tiny differences relative to someone who stays home. At first, this would be a curiosity. Later, perhaps, it becomes part of bureaucracy. Birth certificates might include region and clock correction. Long-distance contracts may specify time standard. Medical records may distinguish biological age, legal age, and synchronized ring age. On such a world, relativity becomes paperwork. But we must keep the scale honest. The time difference between inner and outer edges of a habitable ring world around an ordinary star would probably not create dramatic human aging differences across short periods. This is not a story where one person walks across a bridge and returns 10 years younger. To get large time dilation, you need either extremely high speed close to the speed of light, or extremely strong gravity near compact massive objects like black holes. A ring world rotating for comfortable gravity around a sun-like star may move very fast by human standards, but still far below the speed of light. The relativistic effects are real, but small. The wonder lies not in drama, but in precision. Nature often hides its deepest strangeness in tiny measurements. The universe does not need to shout to be profound. Still, even small effects accumulate. Over one day, the difference may be microscopic. Over a year, still tiny. Over centuries, it may become meaningful to clocks, archives, and scientific instruments. Over the lifetime of a civilization, the accumulated difference becomes part of history. Imagine a monument built at the inner edge and another at the outer edge, both inaugurated at the same standard moment. 10,000 years later, their local atomic clocks disagree by a measurable amount. The monuments have shared the same star, the same ring, and the same civilization, yet they have experienced slightly different amounts of time. Not enough for mythic immortality, but enough to say, the same world did not age as one. There is a quiet emotional power in that. On Earth, we often think of time as the one thing everyone shares equally. Rich or poor, young or old, near or far, the same second seems to pass for all of us. Relativity breaks that intuition. Time is local. Time belongs to paths through space-time. Your clock measures your journey, not a universal flow. A ring world makes that truth visible in architecture. It turns relativity into geography. The inner edge and outer edge are not merely places. They are slightly different histories. Now imagine a scientist on the ring world whose life's work is to measure this difference. She is born in a city near the middle band, where the artificial gravity feels almost perfectly Earth-like, and the climate is carefully moderated. As a child, she looks up at night and sees the far side of the ring glowing faintly across the sky. Her teacher tells her that the people living there are not in the past or future, but their clocks are not identical to hers. She cannot stop thinking about it. Years later, she joins an expedition carrying ultra-precise clocks from the inner edge to the outer edge. The journey is not just travel. It is a pilgrimage across time gradients. They move through farming belts, ocean channels, maintenance deserts, radiation-shielded zones, and cities built under golden starshade patterns. Everywhere people live normally. They laugh, work, sleep, complain about weather, celebrate festivals, and forget that beneath their ordinary lives Space-time is being measured. When the scientist reaches the outer edge, she compares the transported clock with the local standard. The difference is tiny. To ordinary people, it feels like nothing. But to her, it is a revelation. It is the ring speaking in the language of Einstein. The numbers show that the outer edge has not experienced time exactly like the inner edge. The effect is small, but it is real. She looks back across the width of the ring and realizes that civilization has been living on a clock with thickness. The world is not simply broad in space. It is broad in time. And yet, this is only one layer of the ring world's strangeness. There are also tidal effects from the star. Across the ring's width, the star's gravitational pull changes slightly. Across the height of mountains or atmosphere, effective acceleration changes. The ring must hold an atmosphere against artificial gravity, prevent it from leaking over the edges, and perhaps use enormous walls rising along the inner and outer boundaries. These walls, sometimes imagined as rim walls, would themselves be colossal engineering structures. They would help contain air and oceans, but they would also mark the edges where time and environment shift. Standing near such a wall, a person might feel they are at the border not only of land, but of a slightly different clock domain. Atmosphere on a ring world is another miracle hiding inside a problem. On Earth, the atmosphere clings to the planet because gravity pulls it downward. On a rotating ring world, artificial gravity pushes air against the inner surface, but the edges are dangerous. Without containment, gas would escape sideways into space. Huge walls, magnetic fields, atmospheric management systems, or enclosed structures may be needed. Weather would be unlike Earth's weather because the surface is not a sphere. Wind patterns, Coriolis effects, heating zones, and artificial day-night cycles would all interact. Storms might stretch across distances larger than planets. Clouds might form under engineered skies. Rivers might flow outward according to the artificial gravity slope, or be guided by design. Oceans might need basins shaped not by natural geology, but by civilizational intention. Every lake is a decision. Every mountain is either manufactured or captured material arranged by engineering. On a ring world, geography is architecture. The more we think about it, the more the word world becomes almost misleading. A planet is born from collapse, impact, cooling, chemistry, and time. A ring world is built. It is a decision made visible at astronomical scale. Someone, or something, must mine planets, dismantle asteroids, process material, manage energy, fabricate supports, assemble segments, spin them up, stabilize the structure, and protect it from debris. A ring world is not simply an object. It is evidence of a civilization so advanced that its engineering changes the star system itself. And if such a civilization is advanced enough to build it, it is surely advanced enough to know about relativity. They would not accidentally discover that time differs after construction. They would design with it from the beginning. The time gradient would be part of the blueprint. But imagine early settlers arriving after construction, not as the builders, but as inheritors. They may not fully understand every system. They live on the ring as ancient people lived on Earth, trusting the ground without understanding its deep mechanisms. Over generations, myths form. The inner edge may be called the dawnward border because it feels closer to the star's authority. The outer edge may be called the slow rim because ancient clocks there seemed to lag behind. Pilgrims may travel across the ring to gain time, even though the effect is tiny. Religious calendars may differ. Scientists may spend centuries separating myth from measurement. The ring world becomes not only a physics object, but a cultural engine. Relativity becomes folklore. This is one of the most fascinating possibilities. Advanced physics could become ordinary culture. People on Earth once saw eclipses as omens before they became predictable celestial events. On a ring world, time dilation may follow a similar path. At first, mysterious clock disagreements. Then mathematical explanation. Then engineering correction. Then cultural metaphor. Lovers separated across the ring might say, "Your city's clocks run softer than mine." Parents might tease children who move to the outer edge, "You are trying to stay young." Writers might build poetry around edge time. The scientific fact is small, but the human meaning grows around it. Now, let us step back and ask, could the time difference ever become large enough to shape society in a major way? around a normal star at a comfortable distance, probably not in a biological sense. But if the ring world were built in a more extreme environment, the answer changes. Suppose the ring is built around a compact object, like a white dwarf, neutron star, or black hole. Now gravity becomes stronger. Time dilation can become much more significant, but the cost is enormous. Radiation, tidal forces, orbital stability, energy management, and survivability become far more dangerous. A ring world around a black hole is a much more extreme speculative structure. It could produce dramatic time differences, but it would also face hazards beyond ordinary engineering imagination. The closer you go to strong gravity, the more time bends, but also the more nature sharpens its teeth. A white dwarf ring world might be smaller than a sun-like ring world because the habitable zone could be closer in, depending on the star's luminosity. That means less material might be required, but the environment could be harsh and the star's history violent. A red dwarf ring world might also be more compact, because red dwarfs are cooler and dimmer, but red dwarfs can produce flares, and a close-in structure would have to handle magnetic storms and radiation. A ring world around a sun-like star may require almost unimaginable material, but it offers a stable, familiar light source. Every star type changes the balance. The time difference between inner and outer edges is not a universal number. It is a fingerprint of design. Let us return to the classic idea: a huge ring at roughly Earth-like distance from a sun-like star. In such a design, the ring must rotate to create artificial gravity. If it aims for Earth-like gravity, the tangential speed could be enormous by human standards, possibly over 1,000 kilometers per second, depending on the radius. That is far faster than any ordinary human vehicle, faster than planets orbiting the sun, fast enough that relativistic corrections are no longer laughable, though still small compared with light speed. The entire inhabited band is a moving world, and across its width, the outer edge moves slightly faster. If the width is large, the speed difference becomes measurable, so the outer edge's clocks lose a little more time to velocity. Meanwhile, the inner edge's clocks lose a little more time to stellar gravity. The final clock rate becomes a sum of effects. Here is the key conceptual twist. There is no single reason time differs. It is not only because one edge is closer to the star. It is not only because one edge moves faster. It is because a real ring world forces both general relativity and special relativity to speak at once. If you ignore gravity, you may choose the outer edge as slower. If you ignore rotation, you may choose the inner edge as slower. But the universe ignores neither. It combines them. A correct answer must ask for the full geometry of the ring, the rotation rate, the mass of the star, the reference frame, and the method of comparison. This is why simple answers fail. A ring world is too large for simple thinking. And there is another subtlety. In relativity, comparing clocks is not always as straightforward as placing them side by side in imagination. To compare two distant clocks, you must define how they are synchronized. You must account for signal travel time. You must specify a frame of reference. A clock on the inner edge and a clock on the outer edge are not merely sitting in a static gravitational field, they are part of a rotating system. If you physically carry one clock to the other, the clock's path matters. If you compare them by exchanging light signals, signal timing matters. If you use a central reference frame tied to the star, rotation matters. If you use local rotating coordinates, synchronization around the ring may become non-intuitive. Time difference is real, but the way you describe it depends on the operational method. On a ring world, even asking which clock runs slower requires careful meaning. This does not make the effect unreal, it makes it richer. Physics often works this way. The universe gives clear local laws, but global comparisons require definitions. Every person's own clock measures proper time along their path. That is real. A person living on the outer edge follows a different path through space-time from a person living on the inner edge. Over time, their accumulated proper times may differ. That is the heart of the matter. The ring world is a collection of paths. The star curves space-time. The rotation tilts world lines through space-time. The inner and outer edges are not just different radii. They are different histories traced through the four-dimensional fabric of the universe. Now imagine a map of the ring world used by navigators. It does not only show continents, oceans, climate zones, cities, and transportation routes, it also shows time correction contours, lines of equal clock rate curve across the inhabited surface. The map may have soft bands labelled with relativistic offsets. A transport captain planning a journey from inner agricultural zones to outer observatory platforms must account for arrival time in multiple standards. A spacecraft launched from the outer edge begins with a higher tangential speed than one launched from the inner edge. That could be useful. Launching from the faster outer rim might provide more initial velocity relative to the star, depending on direction. But it also means timekeeping and trajectory planning must account for motion precisely. Space travel from a ring world would be both easier and harder. Easier because the structure already has enormous rotational speed, harder because that speed is dangerous and must be managed. If a ship detaches from the ring, what happens? It no longer follows the floor's forced circular path. It moves according to its velocity and gravity. A person standing on the ring is constantly being forced into circular motion by the structure. A free spacecraft leaves that constraint and follows an orbit or trajectory determined by its launch conditions. If launched incorrectly, it could drift away, collide, fall toward the star, or cross dangerous paths. The ring's rotation is not just background. It is stored kinetic reality. Everything attached to the ring shares it. Everything released must deal with it. This is another reason precise clocks matter. Navigation at such speeds requires knowing exactly when and where launch occurs. A tiny timing error can become a vast positional error over astronomical distances. Now, let us speak of materials, because no realistic ring world discussion can avoid the terrifying question, what could hold it together? A rotating ring under artificial gravity would experience colossal tensile stress. Every part wants to fly outward. The structure must pull itself into a circle. The material must endure forces far beyond ordinary engineering. Known materials are nowhere near sufficient for many classic ring world designs. This is not a small obstacle. It is one of the biggest reasons ring worlds remain speculative megastructures rather than realistic human projects. Even if we had the energy and mass, the strength requirement is devastating. You would need exotic materials, active support systems, dynamic stabilization, or a design made of many independent orbiting habitats rather than one rigid ring. The true monster is not only relativity, it is stress. And this gives us another twist. The time difference between inner and outer edges might be scientifically fascinating, but it is not the first thing that would kill a poorly designed ring world. Structural failure would, thermal expansion would, debris impacts would, radiation storms would, atmospheric leakage would, stability problems would. A ring world must survive micrometeorites, comets, asteroids, solar activity, internal earthquakes of stress, and the simple cruelty of scale. Relativity whispers, engineering screams. But the whisper still matters, because a civilization capable of answering the scream must also answer the whisper. Advanced engineering does not get to ignore tiny effects. The larger the machine, the more tiny effects become system-level facts. A ring world might be divided into segments rather than built as one continuous rigid band. Each segment could orbit or be actively supported, creating something more like a swarm or necklace of habitats. In that case, the time differences would depend on each segment's orbit and motion. A true rigid ring rotating as one structure is the cleanest thought experiment, but perhaps the hardest engineering challenge. A swarm of habitats could be more realistic, but it loses the single continuous world feeling. Yet, even in a segmented ring, inner and outer portions can experience different velocities and gravitational potentials. The core lesson remains. Around a star, scale turns relativity into geography. Now, let us return to the human experience. Suppose you are walking at night near the middle of the ring. The star is temporarily hidden by shadow structures, so the sky is dark. But above you, far overhead, the opposite side of the ring glows faintly, a luminous band of settlements, oceans, clouds, and reflected light. It is not a moon. It is your own world, returning to your eyes after crossing astronomical distance. You know that what you see is delayed by light travel time. You are looking not at the far side as it is now, but as it was when its light began the journey. Even vision becomes time travel. Every glance across the ring is a look into the past. If the ring is vast enough, the delay might be minutes or more. A festival on the far side may appear to you after it has already changed. A storm may be visible after it has moved. A city may shine in your sky as a slightly older version of itself. The ring world does not just contain time dilation. It makes delay visible. On Earth, when we look at the moon, we see it as it was about a second ago. When we look at the sun, we see it as it was minutes ago. On a ring world, parts of your own civilization may be far enough away that their light is delayed dramatically. The sky becomes an archive. The far arc overhead is not only distance, it is memory. And because different regions have slightly different clock rates, the relationship between what you see, when it happened locally, and when it arrives to you becomes a sophisticated dance. Astronomers on the ring world would need to teach citizens that the sky is not a single present moment. It is layered time. This connects beautifully to the philosophical heart of the story. We often imagine the present as a universal surface slicing across the universe. But relativity teaches that simultaneity is not absolute. Different observers can disagree about whether distant events happen at the same time. On a rotating ring world, this becomes practical. The civilization may define an official present for convenience, but physics does not hand them one simple cosmic now. The official present is a construction, a useful agreement. It is a treaty between clocks. In ordinary life, that treaty works well enough, but under the surface, every clock keeps its own truth. Would people feel disturbed by this? Perhaps at first, the idea that your friend across the ring is not sharing exactly the same now can be unsettling. But humans are adaptable. We already live with time zones, calendars, leap years, and digital synchronization. A ring world culture would grow around its physics. Children would learn time gradients the way children on Earth learn seasons. They might not find it strange. They might find our planet strange, a tiny natural ball where people once believed time was universal because their world was too small to reveal otherwise. To them, relativity would be part of common sense. Now, consider medicine. Biological processes depend on local proper time. A heart beats according to the time experienced by the body. Cells divide according to local chemistry. If two people live permanently in regions with slightly different clock rates, their biological aging relative to a shared external standard could differ. But again, for a sun-like ring world, the difference across the width would likely be very small. However, precise medicine might care. Long-term studies, generational genetics, radiation exposure records, and drug timing could include local time correction. Hospitals might use local proper time for treatment, but convert records to ring standard time for interregional databases. A patient transported from inner edge to outer edge may have devices that automatically shift timing standards. Pacemakers, neural implants, sleep regulators, and embryo labs may all need synchronization protocols. Relativity becomes part of healthcare. Now, consider law. Suppose a person lives near the outer edge, where clocks run slightly slower relative to the inner edge. If legal adulthood is defined by years, whose years? Local years? Ring standard years? Biological years? Suppose a prison sentence is served in a slower time region. Does the sentence end by local time or central standard time? Suppose a company stores data in an archive near a region where time passes slightly differently. Are expiration dates measured by local clocks? These questions sound absurd until a civilization must answer them. The physics may be tiny, but law is built from definitions. A tiny time difference becomes important when fairness is at stake. Now consider religion and philosophy. A ring world around a star is already a sacred image waiting to happen. Life wrapped around light. The star at the center may become a symbol of origin, power, or divine fire. The inner edge, close to the star, may be considered spiritually privileged by some cultures. The outer edge, aging slightly differently by motion, may be seen as a place of patience or preservation. Some may travel outward for long retreats, believing they are stepping into slower time. Others may reject such symbolism and insist on scientific clarity. The same fact can become ritual, metaphor, or political argument. A world this large would not have one culture. It would have many, each interpreting time through its own stories. Now let us ask a sharper scientific question. If the outer edge moves faster, does that mean it is always more time dilated than the inner edge? Not always. The gravitational effect depends on the star's mass and the radial separation between edges. The velocity effect depends on angular speed and radius. If the ring is rotating slowly, or if artificial gravity is weak, the motion difference may be small. If the ring is extremely close to a massive star, the gravitational difference may dominate. If the ring is very wide, both effects grow in importance. If the ring's design uses active gravity or non-rigid rotation, the result changes. So the most honest answer is conditional. A ring world would experience time differently on its inner and outer edges, yes, but the direction and size of the difference require the design details. The title is true in the deep sense. Time would not be perfectly uniform. But the winner of the clock race is a calculation, not a slogan. This is important because science communication must resist the temptation to oversimplify wonder. It is easy to say, the inner edge is closer to the star, so it ages slower. It is also easy to say, the outer edge moves faster, so it ages slower. Both statements capture one effect and miss the other. The real universe is not obligated to be simple for our storytelling. It is more interesting than that. It lets two correct ideas compete, and the final truth emerges from their combination. That is why this topic is so powerful. It teaches not only relativity, but intellectual humility. In cosmic engineering, one effect is never alone. Now, imagine the ring world's central universities. Students train in chronogeography, the study of time variation across inhabited space. Their textbooks include maps where altitude, radius, velocity, gravitational potential, and clock rate are combined. Architecture students learn how building height slightly affects time, though only by tiny amounts. Transportation planners learn that high-speed radial trains alter passenger proper time by minuscule but measurable amounts. Astronomers learn to correct observations for the ring's rotation. Historians learn to convert ancient records from obsolete local time standards. The civilization becomes fluent in time the way sailors became fluent in wind. A train across the ring would be especially interesting. Suppose a high-speed train travels from the inner edge to the outer edge. It starts in a region closer to the star and slower in tangential speed. As it moves outward, it enters regions of higher tangential speed because the ring itself is moving faster there. The train must match the local ground speed if it is to dock safely. This means transportation across the width is not only about moving north or south in a landscape, it is about changing rotational speed. Massive transport systems would need to exchange angular momentum. Energy costs could be enormous unless carefully engineered. Elevators, maglev tracks, or moving platforms may gradually accelerate passengers to the correct local velocity. If this is done too quickly, passengers feel forces. If done slowly, the journey takes longer. Every cross-ring journey is a mechanical negotiation with rotation. And because motion affects time, the passenger's own clock follows a path through varying velocities and gravitational potentials. A tourist travelling from inner to outer edge and back accumulates a slightly different proper time than someone who stayed home. Again, tiny, but measurable, with advanced clocks. Travel agencies might even advertise relativity tours, not because you gain meaningful youth, but because you can carry a clock and watch the universe disagree with itself by a fraction. Luxury tourism on a ring world might include standing at the exact radius where gravity-based and velocity-based time effects balance, a place where the clock rate matches some chosen reference. People might visit it as the equal timeline, a quiet monument to the balance of Einstein's two great insights. Could such a balance line exist? Depending on design, yes. Across the ring's width, one effect may gradually increase while another decreases. There may be a radius where their combined time dilation relative to a reference equals a selected standard. It would not be magical, but it would be conceptually beautiful. A city built there might call itself Meridian, or the Clock City, or the Still Band. Its identity would come from being neither inner nor outer, neither dominated by gravity nor motion, but balanced between them. Of course, the exact balance depends on reference frame and chosen standard. But civilizations love symbolic centers, even when physics is subtle. A ring world would offer many such symbols. Now consider energy. The star provides enormous power. A ring world could capture a significant fraction of stellar output if it surrounds the star broadly enough. But capturing sunlight is not the same as using it safely. Too much heat must be radiated away. A ring world that intercepts stellar energy must manage thermal balance, or it cooks. It needs radiators, reflective systems, heat transport networks, perhaps enormous dark side panels or high emissivity surfaces. The inner edge may receive more intense radiation and require more cooling. The outer edge may have different thermal needs. Heat itself becomes part of timekeeping indirectly because temperature affects physical clocks unless they are carefully controlled. Atomic clocks, optical clocks, quantum systems, and communication lasers all need stable environments. On a ring world, precision timekeeping is also thermal engineering. The star is not perfectly constant either. Stars have activity, flares, magnetic cycles, radiation changes, particle winds. A sun-like star is relatively stable compared with more active stars, but it still varies. A ring world must monitor the star continuously. If the star brightens in a region or produces a storm, shields must respond. The inner edge may be more vulnerable to increased radiation. The outer edge may have slightly more buffer, but only slightly depending on width. A civilization wrapped around a star lives with the star not as a distant object, but as an enormous neighbor inside the walls. The central fire is both mother and threat. Now we can see that the phrase built around a star hides an entire relationship. The ring world is not merely near the star. It is arranged around the star's gravity, light, radiation, and time curvature. The star defines the ring's reference environment. It bends space-time. It provides energy. It threatens destruction. It becomes the center not only geometrically but physically. If clocks differ across the ring, the star is part of that difference. Even when the velocity effect dominates, the star's gravitational field is still there, shaping the calculation. The ring world is a clock built in a star's shadow. What would the sky look like at the inner and outer edges? If the ring has rim walls, the edge sky may be dramatic. One side could be dominated by a towering wall rising into darkness, perhaps thousands of kilometers high, if needed to contain atmosphere in certain designs. The starward view may be controlled by shades. The far edge may be hidden by haze, distance, or curvature. In the middle, the land may seem endless. Near the edges, people may feel the architecture more strongly. They live near the boundary of the world. Perhaps the inner edge cultures are more aware of the star, with observatories, radiation temples, power stations, and heat management towers. The outer edge cultures may host launch facilities, deep space ports, cold observatories, and long-term archives. The time difference, though tiny, becomes part of this environmental identity. The outer edge as an archive is an interesting idea. If time runs slightly slower there, one might imagine storing delicate records, biological samples, or long-duration experiments. But the practical advantage would likely be tiny compared with environmental control. Still, cultures may value symbolism over practical gain. A civilization may place memorial libraries at the slower edge, not because it meaningfully preserves books longer, but because it represents patience. Science and symbolism often coexist. A place can be technically ordinary and culturally profound. Now, let us be careful about another misconception. If the outer edge moves faster, does a person there feel a wind of time? No. Motion-based time dilation is relative to comparison frames. Locally, physics behaves normally. A laboratory on the outer edge can perform chemistry, biology, and mechanics as usual. The speed is not felt as speed because everything nearby shares it. You feel acceleration from rotation as artificial gravity, not the constant sideways velocity itself. This is similar to being on Earth. Earth rotates and orbits the Sun, and the Sun orbits the galaxy. But you do not feel these velocities directly. You feel local gravity, not cosmic speed. On the ring world, people feel the floor pressing upward, perhaps Coriolis effects when moving large distances or at high speed, but they do not feel their clock running slow. Time dilation is discovered by relationship, not sensation. Coriolis effects could be important. On a rotating habitat, objects moving relative to the surface can appear to curve. In a small rotating station, Coriolis forces can be noticeable and uncomfortable. In an enormous ring world, if the radius is huge, Local curvature and rotation rate may be gentle, so everyday effects could be small. But large-scale transport, weather systems, artillery, aircraft, and ocean currents might still be affected. The rotation shapes motion. The artificial gravity is not identical to planet gravity because it arises from rotation. Engineers and meteorologists must account for this. A thrown ball may behave almost normally locally, but high-speed travel across the ring or along the circumference reveals the rotating frame. Again, the world feels ordinary until scale exposes the machinery. Now think about oceans. A ring world with Earth-like artificial gravity could hold water against its inner surface. But oceans would need basins and boundaries. Waves would travel across designed coastlines. Tides from the central star might exist, but not like Earth's lunar tides. The gravitational geometry is different, and artificial gravity dominates local down. Still, the star's gravity varies across the structure and may introduce subtle stresses and fluid effects. If there are moons, planets, or other masses in the system, their gravity could perturb the ring. Even the distribution of mass on the ring itself matters. Large cities, oceans, and mountains are not negligible if the structure must remain balanced. Moving mass around the ring could affect stability. A civilization may regulate megascale construction to avoid imbalance. Timekeeping, mass distribution, and control systems become linked. Suppose one edge becomes heavily industrialized, adding huge mass to the outer rim. Does that change rotation? Stress? Local gravitational fields? Slightly, yes, depending on scale. A ring world is so large that local mass concentrations may be small relative to the whole. But over time, civilization can move astonishing amounts of material. If they mine asteroids and deposit them on one region, the ring's balance changes. Active systems compensate. But compensation requires timing. Sensors must detect mass shifts, clocks must align, correction impulses must be coordinated. The more we think, the clearer it becomes. The ring world lives only because it is constantly measured. Now let us ask whether a ring world could use real gravity instead of rotation. Could it be massive enough that its own gravity pulls people to the surface? Perhaps in some designs, but a thin ring's gravity would not naturally provide Earth-like downward force toward the inner surface in the simple way a planet does. A massive ring has complex gravitational fields, and if you are on its inner surface, the ring's own gravity may not conveniently pull you down in the desired direction. Rotation is the classic solution because it creates effective outward acceleration. But rotation brings time dilation and stress. Every solution creates new problems. A ring world is a chain of trade-offs. There are alternatives: Banks orbitals, Stanford torus structures, O'Neill cylinders, Dyson swarms, shell worlds, orbital habitats. Many are more plausible than a full rigid ring world. A Dyson swarm, made of countless independent habitats around a star, may avoid impossible material stress and allow flexible orbits. In such a swarm, time differences would exist between habitats, depending on their orbits and gravitational potentials. But the continuous landscape of a ring world has a unique emotional power. It offers the dream of walking around a star, of a single unbroken world with the area of millions of planets. That dream is why we keep returning to it, even when engineering says no. A ring world also forces us to confront scale beyond instinct. Humans evolved on landscapes where a mountain is large, an ocean is vast, and a planet is almost unimaginable. A ring world makes a planet feel like a pebble. The circumference could be so long that a civilization might expand for thousands of years and still not fill it. Entire histories could unfold in regions that never meet. Languages could evolve. Nations rise and fall. Religions bloom and vanish, all on the same structure under the same star, separated by distances so huge that they become practically different worlds. And across this immensity, time itself is not perfectly uniform. The ring world is a continent of clocks. Imagine historians trying to reconstruct events across the ring. A war begins near the inner edge. A discovery occurs near the outer edge. A message travels between them. By the time it arrives, local dates differ, signal delays intervene, and clock standards require conversion. Historical truth becomes four-dimensional bookkeeping. A historian cannot simply write "at the same time." They must specify whose same time. They must ask which signal reached whom, in what order, under what time convention. Relativity complicates history, but it also makes it more precise. A mature ring-world civilization may become very careful with time language. Their historians may be better physicists than our historians need to be. Now think about music and art. On a ring world, composers might create pieces synchronized across cities, separated by light minutes, where each region plays according to delayed signals and local clock corrections. The performance is not heard all at once by anyone, but exists as a space-time artwork. Artists might use the time gradient across the ring as part of installations, clocks lined across a radial avenue, each one adjusted to show both local time and accumulated difference from a standard. Children might stand before them and watch identical seconds tick in slightly different cosmic meanings. Art would help people feel what equations describe. Now, let us go deeper into the actual physical intuition. In special relativity, the faster an object moves relative to an inertial frame, the less proper time it accumulates compared with a slower object between comparable events. On the ring world, the outer edge has a larger radius from the rotation axis. If the angular velocity is the same, velocity equals angular velocity times radius. Increase radius, increase speed. That part is simple. In general relativity, time runs slower, deeper in a gravitational potential. Closer to the star means deeper potential. So across the ring's width, gravitational clock rate increases outward, while velocity-based clock rate decreases outward if speed increases outward. The combined result is a balance. In weak fields and modest relativistic speeds, one can approximate both effects. But the concept matters more than the math. The ring is a place where two relativistic gradients oppose or reinforce depending on design. If the ring is rotating specifically to create artificial gravity, there is a relation between angular velocity, radius, and perceived acceleration. For a given artificial gravity, a larger radius allows a smaller angular velocity, but the tangential speed can still be very large because the radius is enormous. In a giant ring at Earth orbit scale, the rotational period might be days rather than minutes, but the rim speed could be huge. That is another counterintuitive twist. Slow rotation does not always mean slow linear speed. A giant wheel turning once every several days may have an edge moving at incredible speed because the circle is so large. If you stand on it, the sky may not spin rapidly, but the ground is racing through space. This matters for time. People often associate relativity with things moving close to light speed, and it is true that large effects require enormous fractions of light speed. But small effects exist at all speeds. A car, a satellite, a planet, a rotating ring, all have some time dilation from motion. Usually it is too small to notice. But advanced clocks reveal it. A ring world does not need to approach light speed to have real relativistic corrections. It only needs precision and scale. That is why the concept is scientifically meaningful, without becoming exaggerated. Now, let us imagine a simple daily scene. A family sits for dinner near the outer edge. The room is warm. The star's light has been softened by atmospheric filters. A child asks why the clock on the wall has two displays. One shows local time. The other shows ring standard time. The parent explains that local time is the time their bodies live by, while ring standard time is the time used to talk to distant cities. The child asks which one is real. The parent pauses. Both are real, they say. The universe does not have one master clock. It has relationships. The child looks confused, then accepts it, because children can accept wonders. Adults resist. Outside, the far band of the ring glows in the night sky, carrying other clocks, other dinners, other children, asking the same question. This is the meditative heart of the ring world. It turns a difficult idea into a lived environment. We do not merely learn that time is relative. We imagine people building homes inside that fact. We imagine a civilization whose architecture makes Einstein domestic. Now, let us address another possible confusion. If the ring world is built around a star, would the star's gravity pull people inward toward it? Yes, the star's gravity exists. But for people on the rotating ring's inner surface, the artificial gravity from rotation must dominate or be designed to provide the desired effective weight. The star's gravity points toward the star, which is opposite the outward artificial gravity direction on the inner surface. Depending on the rotation and radius, The effective gravity people feel is the result of the rotating frame and gravitational influences. In many simplified ring world descriptions, rotation is chosen so that the outward effective acceleration provides Earth-like gravity against the ring's floor. The star's gravity is comparatively small at Earth-like distance compared with Earth's surface gravity, but not zero. It affects orbital mechanics, stress, and time. So even the feeling of weight is a designed result, not a natural gift. If you moved inward toward the star, artificial gravity would change because your radius changes. The star's gravity would also strengthen. The net effective acceleration could vary. This means the ring's cross-section may need engineering to keep living zones comfortable. Perhaps the inhabited surface is not a simple flat strip, but a shaped landscape, where floor angles, structural supports, and atmospheric pressure are managed. Perhaps the inner and outer edges are not equally habitable. Perhaps most people live in a central belt, where conditions are optimized, while the edges host industrial zones, observatories, ports, and scientific stations. The title speaks of inner and outer edges, but real civilization may avoid extreme edges for ordinary living. Edges are often where worlds reveal their machinery. Now, let us think about clocks physically placed at different heights above the surface. On Earth, a clock on a mountain ticks slightly faster than one at sea level, because it is farther from Earth's center and experiences slightly different gravitational potential. On a ring world, height above the surface changes radius too. A tower extending inward toward the star, would be at a smaller radius, moving slightly slower with the ring, but closer to the star. A deep underground facility, outward through the ring's thickness, would be at a larger radius, moving faster and farther from the star. Even vertical architecture could have time gradients. A skyscraper on a ring world might have floors that differ in clock rate, in a way combining rotation and gravity. The differences would be tiny, but with precise clocks, measurable. Imagine luxury hotels advertising rooms at different chronometric altitudes. Again, absurd for daily life, meaningful for science. Now bring in quantum clocks. Advanced civilizations may use optical lattice clocks, or even more precise timekeeping technologies. Such clocks can detect tiny differences in gravitational potential. On Earth, precision clocks can measure height differences by time rate differences. On a ring world, chronometric surveying could become a way to map the structure. Instead of only measuring distance with lasers, engineers could measure clock rates to infer gravitational and rotational conditions. Time becomes a diagnostic tool. If a region's clock rate shifts unexpectedly, it may indicate structural movement, mass redistribution, or rotation change. The ring could be monitored through time itself. In a poetic sense, the world's health is heard in its ticking. But what happens if the ring's rotation changes? If engineers slightly speed up or slow down the ring to adjust artificial gravity, velocity-based time dilation changes across the entire structure. The clock network must update. The artificial gravity changes, stress changes, weather changes. Ocean levels might shift, transportation systems recalibrate. A ring world cannot casually adjust its spin. It has enormous angular momentum. Changing it requires vast energy and careful control. But over long times, perhaps small adjustments are necessary due to mass redistribution, stellar evolution, or engineering maintenance. A spin correction century might be a major historical era. People may remember when the gravity was slightly lighter, when clocks were recalibrated, when the standard calendar changed by fractions. Again, scale turns technical adjustments into culture. Now, let us think about stellar evolution. A star changes over time. A sun-like star slowly becomes brighter over billions of years. A ring world designed for long-term habitation must adapt. It may move, adjust reflectivity, alter shade patterns, expand habitats, or migrate populations. If the ring changes radius, rotation must change to maintain artificial gravity. And time dilation changes as well. A ring world is not only a structure in space, it is a long-term conversation with a changing star. Over millions of years, the star's luminosity and gravitational mass loss through radiation and wind may alter conditions. The ring's clock system evolves with the star. The civilization may measure epochs not only by political history, but by stellar aging. This gives the documentary a larger perspective. Even a ring world is temporary. It may last millions or billions of years if maintained, but stars evolve, Materials fatigue, civilizations change, impacts happen, entropy works patiently. The ring world may feel eternal to its inhabitants, but it is still inside time. And beautifully, its inner and outer edges experience that time slightly differently. The structure that tries to master a star cannot escape the universe's deeper rules. Now imagine a future archaeologist, long after the original builders are gone, exploring abandoned sections of the ring. The cities are silent. The star still burns. Clocks in sealed vaults still tick, powered by ancient systems. Some are near the inner edge, some near the outer edge. The archaeologist compares them and finds the accumulated signature of millions of years of differential time. The clocks are fossils of space-time. They reveal where they lived. Like tree rings record seasons, these clocks record relativistic geography. Even ruins on a ring world would not age identically. Decay itself would have local time. Of course, chemical decay, erosion, and structural degradation depend mostly on local environment, radiation, temperature, and maintenance, not just relativistic time. A warmer inner edge may corrode materials faster, despite perhaps different clock rates. The outer edge may preserve artifacts better because of cooler conditions or lower radiation, not because time is meaningfully slower. We must be careful. Relativity is real, but it is not always the dominant practical factor. In many everyday outcomes, ordinary environmental conditions overwhelm tiny time dilation. This is another scientific twist. The most conceptually profound effect may not be the most practically powerful. The universe can be subtle and still be overshadowed by rust. Now, let us bring the audience back to the central question in a clean way. A ring world built around a star would experience time differently on its inner and outer edges, because those edges occupy different positions in the star's gravitational field and move at different speeds due to rotation. The inner edge is closer to the star, so gravity tends to slow its clocks. The outer edge is further but moves faster, so motion tends to slow its clocks. The combined result depends on design. In many rotating Earth gravity ring worlds, the outer edge may tick slightly slower because of its greater speed. But this is not universal. The effect would be small for ordinary habitable designs around normal stars, but significant enough for precision systems and profound enough for philosophy. That is the answer in one breath. But the full wonder is what this answer does to our imagination. Because now, when we picture the ring world, we no longer see it as a simple band. We see layers of time. We see every city carrying a clock rate. We see every road crossing not just distance, but space-time. We see people living normal lives inside a machine, whose edges quietly disagree. We see a civilization that must build calendars for a rotating universe. We see law, medicine, transport, art, and memory shaped by the fact that time is not one thing. Now let us imagine the first moment the ring world becomes habitable. The builders have spent ages gathering material, perhaps dismantling planets and moons, perhaps guiding asteroids into industrial furnaces, perhaps weaving exotic composites under robotic control. The ring is assembled in segments, then spun up slowly. At first, no one lives on it. It is too dangerous. Test clocks are placed across its width. Sensors awaken. The first atmosphere is released into sealed valleys. Oceans are poured into basins. The ring groans under stress. Stabilizers fire. Shadow panels align. For the first time, artificial dawn sweeps across a landscape that did not exist in nature. Engineers compare the clocks. The inner test clock and outer test clock disagree exactly as predicted. This is the moment the builders know the ring is not only rotating correctly, it is living in relativity correctly. The first sunrise on a ring world is also the first synchronized argument between time and architecture. Then come the settlers. They step onto the inner surface and feel weight. Maybe they cry because after generations in smaller habitats they can walk under open sky. But the sky is not open in the planetary sense. It is engineered openness. The star is controlled. The horizon rises impossibly. The world curves up above them. They carry ordinary human questions. Where will we build? Where will children play? Where will we bury our dead? But beneath those questions are hidden calculations. What is the local acceleration? What is the clock correction? What is the radiation exposure? What is the structural stress? Every home sits on a foundation of cosmic mathematics. As generations pass, the ring becomes normal. This is perhaps the strangest part. The impossible becomes ordinary to those born inside it. Children complain about school while living on a band around a star. Markets open under artificial dawn. Rain falls from clouds grown in engineered circulation cells. Old people sit near windows and watch the far arc of the ring glow across the night. Lovers argue about moving inward or outward. Farmers discuss soil nutrients. Pilots discuss launch windows. Clock engineers discuss relativistic drift. Civilization domesticates the impossible, but the impossible remains there, quiet and enormous. Now, let us explore the psychological difference between inner and outer cultures more deeply. The inner edge, closer to the star, may feel more luminous, more intense, perhaps more tightly managed. Its infrastructure may focus on heat rejection and radiation shielding. Its people may grow up with a stronger awareness of the central fire. The star is not just a light in the sky, it is a presence. The outer edge may feel more connected to deep space. It may host observatories looking away from the star, launch systems, long-range communication arrays, and perhaps colder habitats. Its people may think of themselves as border dwellers, guardians of the outside. The inner edge faces the heart. The outer edge faces the abyss, and between them lies the living band, a world stretched between fire and night. The time difference becomes a metaphor for these orientations. Inner edge time is shaped by nearness to the star. Outer edge time is shaped by speed around it. One is slowed by depth, the other by motion. One belongs to gravity, the other to velocity. Two edges, two ways for time to bend. It is almost poetic, but it is also physics. Now imagine a festival celebrated across the entire ring. Because of light travel delays and clock differences, the festival cannot truly begin everywhere at one physically absolute moment in any simple sense. The central authority may broadcast a signal, but it reaches different regions at different times. They may instead schedule the festival by local clocks corrected to a standard, or they may embrace the delay, letting celebrations sweep around the ring like a wave of light. Imagine billions of people watching as the festival begins near one region and travels across the sky, visible along the rising arc, each city igniting lamps in sequence. The ring becomes a clock made of civilization. Time difference is not hidden, it is performed. Now consider war, though gently, because even peaceful worlds must consider danger. In conflict, timing becomes strategic. Signal delays matter. Clock standards matter. A command sent from one region may be outdated by a rival. Autonomous systems become necessary. Defensive shields against meteors or hostile projectiles must respond locally. A ring world cannot be governed purely from one central point in real time. Its size forces decentralization. Even without politics, physics demands local autonomy. The speed of light becomes a constitutional principle. The clock gradient becomes a military and civil planning factor. This is another twist. The larger a civilization becomes, the less it can pretend that central control is instant. The universe enforces patience. Now return to peace. Scientific observatories on the outer edge may be magnificent, farther from the star by a little, shielded from inner heat, perhaps looking outward into interstellar space. They could use the ring's enormous baseline for astronomy. Telescopes separated by vast distances across the ring could act together, using precise timing to create images of distant objects. But to combine their observations, their clocks must be synchronized with extraordinary accuracy. The same relativistic effects we are discussing become part of the telescope. Without correction, the image blurs. With correction, the ring world becomes an eye larger than planets. It could study exoplanets, black holes, cosmic background radiation, and distant galaxies with unimaginable resolution. Timekeeping becomes vision. And perhaps this is one of the great reasons to care. A ring world is not only a habitat, it could be an instrument. Its size makes it a scientific tool. It can measure stellar behavior, detect gravitational waves, observe the galaxy, test relativity, and conduct experiments impossible on a planet. The inner and outer edge time differences are not a nuisance only, they are data. The ring world can use its own clock gradients to study physics. A civilization living there might understand space-time not as a distant theory, but as the operating system of their home. Now let us ask, what would happen to language? People may develop words for time that we do not have. A word for the difference between local time and ring standard time. A word for the emotional feeling of seeing the far side of your world delayed in the sky. A word for the tiny age difference between friends who move to different edges. A word for the balance radius, where clock effects cancel under a chosen standard. Human languages on Earth developed many words for snow, sea, wind, light, and kinship, depending on culture. A ring-world culture would develop words for relativity. Their poetry might be impossible to translate without physics. Now imagine a quiet poem from such a world. I waited for you in outer time, while you crossed from the starward fields. To us, it sounds metaphorical. To them, it may also be technically true. At this point, we should confront the deepest philosophical result. A ring world built around a star is an attempt to create a world intentionally. Planets are inherited. A ring world is chosen. But even when intelligence chooses the shape of a world, it cannot choose the laws beneath it. It can arrange matter, harness energy, spin structures, shade sunlight, and build continents. But it cannot make time universal. It cannot tell space-time to become simple. The ring world is powerful, but relativity is deeper. The builders can wrap a star, but they cannot wrap the universe around their convenience. This is humbling. The grander the engineering, the more clearly the laws appear. Now, let us imagine the ring world from outside. A spacecraft approaches from interstellar space. At first, the star looks normal. Then, instruments detect something odd. Too much infrared radiation, strange periodic dimming, artificial structures, a thin line crossing the star's light. As the ship comes closer, the ring becomes visible, a dark band and glittering arc around the star. It is so large that the mind refuses it. The ship's clocks compare signals from inner and outer beacons. They detect slight differences. The ring is not only a structure in space, it is a structure in time. The explorers realize that every beacon's timestamp must be corrected before docking. To enter this world, they must first learn its clocks. Docking would be dangerous. The ring surface is moving at enormous tangential speed. A visiting spacecraft cannot simply descend like an airplane to a planet. It must match velocity carefully. The outer edge and inner edge have different speeds. Ports at different radii require different approach profiles. Launch windows are complex. A mistake could be catastrophic. Spaceports might be located on special structures extending from the ring, designed to manage velocity transitions. Travelers arriving from outside may experience the ring's time system before they ever see its forests. The first customs form might ask, "Select arrival time standard." Now, imagine a person from Earth, used to planets, stepping onto the ring. The first shock is the horizon rising. The second is the star's strange position. The third is the clock. Their wrist device shows local time, but the guide explains that it is being corrected for ring position. The visitor laughs, thinking it is unnecessary. Then they tour the clock observatory and see instruments measuring differences smaller than a blink, but more real than opinion. They realize that this civilization has built its daily life around truths Earth people mostly ignore. The visitor feels small, not because the ring is large, but because time itself has become visible. Now let us consider if the ring world could rotate at different rates in different bands to equalize artificial gravity or time. A rigid solid ring cannot have different angular velocities across its width without shear and mechanical conflict. But if the structure is made of independent bands, or layered moving surfaces, perhaps each band could rotate differently. That would introduce enormous engineering complexity at the boundaries. Neighboring bands would slide past each other at high speeds. Transportation between them would require velocity matching. But such a design could tune gravity or time effects differently. Maybe advanced civilizations would prefer segmented rotating bands rather than one rigid plate. Then the inner and outer edge, time difference, could be engineered intentionally. They might reduce it, amplify it, or shape it for specific purposes. Time becomes a design variable. This is a remarkable thought. In natural worlds, time gradients are given by gravity and motion. In megastructures, they may be partially engineered. A civilization could choose rotation profiles, orbital radii, and gravitational environments to create desired clock rates. It could build slow time archives or fast time laboratories, though practical limits remain. To make large differences, extreme conditions are needed, but small controlled differences may still have uses in precision science. A ring world could become a laboratory for clock physics on an astronomical scale. Now, let us think about education again. A teacher stands before students and draws two circles, one for the inner edge, one for the outer edge. She explains that both complete one rotation together, but the outer circle is longer. Then she draws a gravity well around the star, showing that the inner edge sits deeper. The students argue. Some think inner time is slower, some think outer time is slower. The teacher smiles and says, both have reasons. Physics is not guessing which story feels stronger. Physics is adding the effects. The students learn something more important than the answer. They learn how to think when nature gives competing truths. This educational moment mirrors our own. The title tempts us to assume a simple dramatic result, but the deeper answer teaches balance. The ring world is a classroom wrapped around a star. Now, let us explore the ring's maintenance tunnels. Beneath the living surface there may be layers of machinery, structural ribs, heat pipes, magnetic conduits, transportation shafts, radiation shelters, atmosphere processors, water recyclers, sensor arrays, repair robots. In these hidden layers, workers may experience slightly different effective gravity and clock rates depending on depth. The public sees grass and sky. Beneath it is an artificial skeleton. The ring's outer structural layers may move faster than the inhabited surface if they are farther from the center. Clocks in deep maintenance zones may differ slightly from clocks at the surface. Repair crews may carry devices that constantly update their time standard. The ring's hidden body is full of tiny relativistic differences. A ring world also has a problem with impacts. Space is not empty. Dust grains at high relative speeds can be dangerous. Meteoroids, comets, and asteroids threaten the structure. A hole in the ring could release atmosphere, damage cities, or create stress fractures. Defense systems must detect and divert objects. Because the ring is enormous, impacts can occur far from central control. Local defense grids need precise timing and prediction. If an object approaches the outer edge, the relative velocity includes the ring's local tangential speed. The outer edge moving faster may face different impact energies depending on direction. Time, motion, and survival again connect. Now imagine an impact alarm. A tiny object, perhaps only meters across, is detected days before collision. The prediction system calculates where the ring will be, which edge is threatened, what local velocity applies, how signals should be routed, and what clock standard all defense units must use. A delay of milliseconds may matter. The people in the nearby city may never know how many corrections protected them. They sleep under artificial stars while machines adjust for relativity and motion. Civilization often survives because invisible mathematics works. This is true even for us. We live because countless systems function beyond our awareness. Electrical grids, satellites, weather prediction, medicine, agriculture. On a ring world, that hidden dependency becomes cosmic. The ground itself is technology, the clock itself is technology, the sky itself is technology. Now let us return to the idea of a conclusive result. What should the audience remember after the video ends? They should remember that a ring world's inner and outer edges are not equal in time because they are not equal in motion or gravitational position. They should remember that the inner edge is closer to the star, and therefore deeper in gravity, tending to run slower. They should remember that the outer edge moves faster if the ring rotates as one structure, tending to run slower from velocity. They should remember that the final result depends on design, and in many Earth gravity rotating ring concepts, the outer edge may have the stronger slowing due to speed. They should remember that the effect is real but usually tiny, not a fantasy time portal. And they should remember that on a megastructure, tiny effects can matter because civilization itself becomes precise. Now let us deepen the ending with a final journey. Imagine traveling from the inner edge to the outer edge over many days. You begin in the starward lands where the air is warm and golden. The central sun feels psychologically closer, even if still enormously distant. Power towers shine. Heat shields shimmer. The people speak of the star as though it is a neighbor. Your clock records local time. Then you board a slow radial train. It rises outward across the ring's width. Though rises is a strange word here, because up and down are manufactured. The train accelerates gradually to match each new radius. Outside the window, landscapes change. Farms give way to cities. Cities give way to observatories. Gravity shifts by a whisper. Radiation levels change by a whisper. Your clock correction changes by a whisper. Nothing dramatic happens, and that is the most dramatic thing of all. The universe is changing its rules around you so gently that only instruments notice. At night, during the journey, you look upward. The far side of the ring spans the sky. Somewhere on that glowing arc are people whose clocks are running differently from yours. Not enough for them to feel alien. Enough for the universe to be honest. You realize that time is not a background. It is part of the landscape. You are not traveling through space only. You are traveling through the conditions that decide how much time your body will accumulate. When you finally reach the outer edge, you stand near the boundary wall and look outward into deep space. Behind you lies the star, filtered and controlled. Ahead lies darkness, planets, perhaps, comets, the galaxy, and the unknown. Your guide tells you that this edge moves slightly faster than the place where your journey began. Your clock has followed you, carrying the memory of every acceleration, every radius, every gravitational difference. The final offset is tiny, a number on a display, but you feel something larger than the number. You feel the end of the old belief that time is simple. And then comes the last twist. The ring world was built to create more living space, to harness a star, to give civilization room beyond planets. But by doing so, it reveals something planets hide from us. Earth is small enough that we can ignore many relativistic differences in daily life. The ring world is large enough that ignoring them becomes harder. The megastructure does not escape physics. It magnifies physics. It becomes a mirror where the universe shows its deeper face. The builders wanted land, light, and gravity. They also built a lesson. Time belongs to motion, gravity, and path. So, would a ring world built around a star experience time differently on its inner and outer edges? Yes. Not like a magical portal. Not like a movie where one side lives centuries ahead, but in the real, precise, unavoidable way relativity works. The inner edge, closer to the star, sits deeper in gravity and tends towards slower time. The outer edge, moving faster with the rotation, tends towards slower time because of speed. Depending on the ring's design, one effect may dominate. In many giant rotating ring worlds built for artificial gravity, the outer edge could be the slightly slower clock. But the true answer is written in the ring's radius, width, rotation, and star. The edges are not just borders of land, they are borders of clock rate. And in the end, that is more beautiful than a simple answer. A simple answer would make the ring world smaller in our minds. The real answer makes it larger. It lets us see a civilization wrapped around a star, living under engineered dawns, walking on a rotating world, building laws and songs, and observatories around the fact that time has texture. It lets us imagine children learning that clocks are local, lovers separated by light delay skies, scientists measuring tiny differences across continents of metal and soil, and ancient archives preserving the accumulated whispers of relativity. It lets us feel that the universe is not a stage where time flows equally for all actors. The universe is a woven thing, and every path through it has its own thread.